So here, with having the F, the colon, and the A, arrow A, this is saying, hey, we're dealing with a relation on A cross A. In terms of the function notation or terminology, this tells you that the domain of your function is A, and the codomain, or the set that your range lives in, is also A. Okay? Now, in order to be a permutation function, this is a function that is a bijection. Now, if you forget the word bijection, okay. The key words you do need to know here is that your permutation function is somebody that is both one-to-one and onto, and those two sets before and after the arrow both have to be the same. Now, we're going to focus mainly on this course on finite permutation functions, and the nice thing about finite permutation functions is they're written in a very, very specific way, which makes them super duper easy to spot. And in fact, they're written similar, not identical, but similar to what we would do with a relation. Okay? So first, let's talk about the formatting for finite permutation functions. We'll have an example of some finite permutation functions, and then we'll look at the tie-in between our permutation functions and relations, and then move on to some other things we do with our permutation functions. So that's rough outline of what we'll do today. So if we have our permutation function and it's on a finite set, what happens? Our building set A is just some finite set, so standard notation here, A1, A2, all the way to AN. So we have what? We have N objects or N elements in this building set. So this tells you your cardinality of A is N, which is not infinity. And then our function P, which goes from set A to set A, we're going to say that it is a bijection on A. And remember, a bijection is both one-to-one and onto. So that right there is what a bijection is. Key thing to remember is the bi meaning two. Okay, so both one-to-one and onto, two things. Now, in terms of a finite set, you can write it as a collection of ordered pairs, like you would with a relation. But instead, the standard format, well, actually, there's two main standard formats. The first standard format that you normally learn when you deal with permutation functions is a two-row format. So the top row up here deals with your domain, or in terms of relations, this is the first position in the ordered pair. So if you were dealing with an ordered pair AB, that top row gives you all of the different first positions. Okay? Note this particular notation right here, this two-row format, is only something that would make sense if you have a function. Why? Because for functions, every single first position in your ordered pair has exactly one second position. This format doesn't make sense if you have two second positions corresponding to one first position, because it wouldn't look like a matrix. Okay, so this guy looks like a two-row matrix. Now, the second position down here, with these fancy terminologies, symbols of P of A1, P of A2, or really standard function notation, those guys are your range, or if you will, the little images of each one of the elements A1 through AN. In terms of ordered pairs, these guys are your second positions. And actually, since we just talked about that relationship between relations and the permutation notation, let me go ahead and get us an extra example right here before we get into the prepped up example. I think that should be enough space. So here, what would this look like? Suppose we are on our building set, oh, I don't know, maybe 1 through 5. For permutation functions, it is standard. You don't have to do this, but it's standard to have the elements of your set 1 through n is often what people will do. And if it's not that way originally, the people will often adjust. It's not a requirement, but it's pretty standard. So here, suppose your permutation function, what would it look like? Well, you'd grab your domain, which is your building set A, And then you'd look at what are all of the guys associated with A. So I'm just going to make up a random example here. So maybe we have somebody like this. In terms of ordered pairs, notice what happens. And I totally did not mean to make that red, so let's make that black to indicate that we're actually doing something here. In other words, the red is the starting point. This corresponds to, take the first column, which is 1, 2. 1 would be acting like your first position. 2 is acting like your second position. Here, with 2, 4, this tells you the first position in the ordered pair is 2, second position is 4. 3, 1, as your first position is 3, second position is 1. 4, 3, as your first position is 4, second position is 3. And lastly, 5, 5 tells you you have the ordered pair of 5, 5. Notice what happens. We take all of our little ordered pairs, and they are stacked in a column. It is a way to write less. And in math, if you can be lazy and still have all the same information there, that is something that often happens, or it is considered advantageous. Depends on how you're actually applying it, but that would be this here, this 2-row format is sort of the condensed way of writing out the ordered pairs that we had from our relation. Again, notice here, if we had a different example, let's assume that we're still on our building set 1 through 5. So let's grab an actual proper relation. In this particular case, if we had a relation, maybe 1, 2, maybe 1, 3, maybe 2, 4, maybe 3, 5, and I'm going to stop at that point. If we tried to write this guy in our 2-column format, at the top, the 2 columns always have, not 2 columns, 2 rows. The top row always has your building set. Below each of these numbers, so this top row is always that building set A. Here, on that second row, is always the second positions. Now notice here, and I'm going to deal with these ones here for the last one to the first one. So 3, 5, that tells you below 3 you should write a 5. 2, 4, before 2 you should write a 4. Now these first 2 ones, it says 1, 3, and 1, 2. This tells you that below 1 you should write a 2 or a 3. Now you're only allowed to write one number, so the question of course is which one do you write? And that's the reason why this 2-row format wouldn't actually work out if you have a normal relation. Notice also you've got these missing pieces over here because we don't even have ordered pairs that start with 4 and 5. Okay? And this is one of the reasons why you're really looking for your function, because you need to deal with the entirety of your domain. Okay? Now, the other thing that you deal with is the fact that it's a bijection. In other words, it's 1-to-1 and onto. It turns out that if you are on a finite set and your function is both 1-to-1 and onto, this is what it means for those outputs. Let's go with this one. All of these numbers right here in that second row, if you are a bijection, a 1-to-1 and onto function, this means that those guys are just the set A rearranged. And this is why it's called a permutation function. Remember back when we were in our counting topics, we talked about permutations, and to permute numbers meant you were just going to rearrange the order. That's where the name comes from. Okay? Now, that gives you sort of a crash course of some of the things that you'll see. Notice this 2-column format right here is pretty darn distinctive. The top row tells you exactly all the numbers that you're going to be dealing with. It tells you your building set. So in actuality, with these guys, you aren't normally given this building set A. This top row gives you that building set A. Bottom row right there gives you the actual function, or completes the actual function, and it should be on a finite, or it will be on a finite set if you actually have a permutation function, just a reordering or a rearrangement of that first row. All right, so that gives you the crash course of what these things can look at. The rest of today is going to be looking at, is there anything weird that happens? What can we do with them? What sort of operations do we have on them? All right, The first example that I've got prepped up for you, and I believe it's actually the only example I've prepped up for you, that way we didn't have the issue where I have to put in extra space, is this next example. So this next example says, all right, we've got the building set 1, 2, 3, so much smaller than the example we just looked at, and we would like to find not just one permutation function on this building set. We would like to find all of the permutation functions on this building set. So if we go and we look for all the permutations on this building set, here's one of the things you can start with. You know for sure with any permutation function on our building set A, if you put it in the 2-row format, and I'm going to put all these guys in the 2-row format until we get to our second standards for permutation function, which is not the 2-row format. It's something different. But we're not there yet. Standards for the 2-row format is you start off and just write your building function or your building set here on the top row. So what's a possibility? And I'm going to send this out to you guys. What is a possibility for this second row? Now remember, the only entries you're allowed to put in the second row are the numbers 1 through 3, and you have to put them all in there. So what do you guys think? For that second row, feel free to just type them out in a list. What is a possibility that we could enter right here? I'll do the first one. So for the first one here, I'll be the super duper lazy. I could put 1, 2, 3. There's one permutation function. Now, suppose you guys want to pick one. What's something that you could put for the entire bottom row? Notice you do have to pick 3 numbers. There we go. Okay. Whew. Now, those are the only 2 permutation functions where you actually write 1 first in the second row. So what happens if we change it up? So what's another option that we deal with on that bottom row? And yeah, we could do 2, 1, 3. You could, yep, I've got extra guesses coming in. I'm going to pull your guesses in a pseudo order here. I think I've got that one. Let me make sure. Do we have all of them? Oh, we're missing one of them. Anybody spot what the last one is? Yep. Now, my claim was that this is all of the possible permutation functions when we're just dealing with the set 1, 2, 3. But you guys check it out. Does it look like we could actually rearrange those numbers 1, 2, 3 in any different a way than what we've just written down there? Is there any possible way to rearrange the numbers 1 through 3 other than what we've just done? Anybody have a guess? Yes or no, and if no, why not? I'm looking here for a tie-in with something we've done in the past, is why that question is leading the way it is. In other words, there's something familiar about what we've just done. It's okay if you don't notice it, though. Ooh. The words you use to guess for that guess aren't the technical words, but you're on the right track. So in this particular case, we've got 2 permutation functions where the second row started with a 1. Well, there's only 2 possibilities. The 2 can come first or the 2 can come second. Same thing happens if you start with a 2. The 1 can come second or the 1 can come third. If you start with a 3, 1 can come first or 1 can come second. The assumption here that we were doing is we had to rearrange all 3 numbers, so that meant we had to use all 3 numbers. And since there were only 3 positions, if you use all 3 numbers, you have to use each number exactly once, which means there is a total of 3 factorial or 6 permutation functions on what? On a building set that has 3 elements. Now, using that information, suppose we had A equals 1 through 5, so the same building set with the last example. Any guesses how many permutation functions there would be on the numbers 1 through 5? Yep, there'd be 5 factorial, and 5 factorial is 120, so we are definitely not going to list all those guys out. When I think it was in grad school when I was just starting to do some of my research, I needed to list out a bunch of permutation functions, and it was big. It was bigger than 5 factorial. It was something like, I want to say they were like length 8 or 10 or something like that. So we were looking at like 8 factorial, 10 factorial, which is crazy big. At that point, you're starting to look at things where you automate it. I had to write a script. I was like, I'm not writing these out by hand. I have to get the computer to help me. But those are some of the things where these guys, permutation functions, there can be a lot of them. So it depends on, do you need all of them? Like here, we listed out all of them, or are you just going to be looking at your specific 1 or 2 that you're dealing with? Okay? And it all depends on what you're doing. For us in this class, most of the time, you're just going to be dealing with 1 or 2 permutation functions and then manipulating it with some sort of operation. But if you need to list them all out, the n factorial there would be telling you how many to go for. It's a nice way to know that you haven't missed anybody. Now, we're actually going to use some of these permutation functions, so let me put some names on them. Okay? And here, I'll go ahead and write P1 for permutation function 1, P2 for permutation function 2, P3 for permutation function 3, P4, and lastly, P5. And notice I totally missed somebody. That's because the first one has a special name. Notice anything that looks distinctive or special about that first permutation function that's different from everybody else? Oh, yeah, I could totally call it P0. So I'll go ahead and put that in there, but it actually has another name that I wanted to talk about. But notice anything special about that first one? You got it. So one of the functions that we talked about last time was called the identity function, and it said when you had your function, the element that was in your domain, so in this case, one of these top ones, the number that was attached to it after it ran through the function, so these guys down here, was the same. In other words, the function didn't change anything. This guy here is replicating that same idea. This guy is called our identity function, and with permutation functions, the special name for it is, and we'll see why this special name is for it in a little bit, is a 1 with 2 parentheses around it. Okay? I'm going to write this as the name here, identity. Or if you prefer, identity function. Okay? So that guy's special. And we'll see why in just a little bit. And we'll also see why this naming convention comes up in a little bit. But I want to give you that naming convention right now so we can get into practice using it. But it is when you write it in the 2-column format without this sort of name attached to it, the top and the bottom row look identical. All right, so let us actually now do some operations. Okay? So first thing, our first question that we want to do is, say we pick on somebody, maybe we pick on function P3, so this guy right over here. And suppose we want to find the inverse function of that guy. Now we've talked about inverse functions before, or I really should say we've talked about inverse relations before. So let's go back and look at this guy with respect to it being a relation, because remember, all functions are relations, so even if you forget everything in this section, okay, that would be problematic. But if you forget, say, most of this stuff with respect to functions, you can pull your functions back to a relation and still do some stuff, okay? So first thing is, let's go ahead and copy down what P3 is. Let me get back to black here. So remember, our P3 was 1, 2, 3, 2, 3, 1, and that just allows me to scroll up here, okay? Now, way 1. And then I'm going to show you the better, faster way when we deal with two rows, but that'll be way 2. Okay? So way 1 is you rewrite your permutation function as a relation. In other words, you put it back into the ordered pairs. Did not want to write an R there. We're just going to get rid of that R. And apparently, not doing it the right way. Yep, definitely didn't do that the right way. Just a second. All right. So write it as a relation. And if we write this function in its ordered pairs, you'll have 1, 2, which is your first column. You'll have 2, 3, which is your second column. And you'll have 3, 1, which is your third column. Now, if you look at the inverse of that relation, remember what the inverse does. The inverse simply swaps your first and your second position. Or in terms of what you would have heard back in like an algebra class, it swaps the x's and the y's, which means this first ordered pair turns into 2, 1. The second ordered pair turns into 3, 2. And the last ordered pair turns into 3, 1. And if we actually, I lied, the last ordered pair should not turn into 3, 1. Actually flip it. So the last ordered pair right there should turn into 1, 3. Actually reverse the order of the ordered pairs there. Which means if you rewrite this guy in terms of in the first position getting bigger, so you get 1, 3, you'd get 2, 1, and 3, 2. And no, you don't actually have to reorder those ordered pairs. I just did that to be consistent. Okay. Then, if we wanted to get our answer back into our 2-row format, the top row or the first row is always going to be that 1, 2, 3. What should we write on the second row or the bottom row for this inverse of the P3? Anybody have a guess? This is just converting the work we've already done back into the 2-row format. Hint, it should be some combination or some arrangement of the numbers 1 through 3. Yep. So we're going to pull these second numbers. So we're going to pull the 3. So 1, 3 tells you 3 should be under 1. 2, 1 tells you 1 should be under 2. And 3, 2 tells you 3 should be under 2. Now, notice you're still on the same building set 1, 2, 3. We've already written out all of the permutation functions on that building set 1 through 3. So this guy should be one of the previous functions that we already found. Anybody spot which previous function it already is? I realize it's not visible, so let me scroll down just a little bit. Yep, it's P4 or that fourth one. So notice if you actually write out all of your permutation functions, whatever manipulation or operation that you do on your permutation functions, your answer is just going to be one of the options. So here we have a grand total of 6 permutation functions on our building set 1 through 3. So regardless of what operations we do with any of these 6 permutation functions, the answer is always going to be only between one of these 6 options. It actually makes it really nice for like multiple choice questions, although to be fair, I've never done multiple choice questions with this topic before. But your multiple choices could be each one of these 3, and then before, it might be saying things like do such and such operation to whatever ones that are picked. Okay. Why? Because these are the only possibilities for your answers. All right, so that was way 1. You pop everything back into a format you already know. You do stuff on the ordered pairs like we've done in the past. And when I say we've done in the past, that you should have had at least one homework question that dealt with this, and we've talked about it a little bit. And then you pull it back to the new format for your permutation function, this 2-row format. Now, that's not the way you normally deal with these guys. So here's how you actually normally deal with calculating the inverse for a permutation function, and I should say a finite permutation function. You start off with the actual permutation function. So this guy right here, And here's the key thing. I'm going to color code these to show you where they go. You flip the rows is what you do. Okay? So notice how I color coded that top row in the original function, permutation function, yellow and blue. Notice here, I'm color coding those new rows that we're going to build down here, also yellow and blue. What did I do? I flipped the color coding. We're going to keep the numbers exactly in the same order in each of these rows. All we're going to do is flip the rows. So 1, 2, 3 from the top row is now going to be in the bottom row. The 2, 3, 1 from the original second row is now going to be in the top row. Do a quick double check, make sure I actually flip the first and second row correctly. That would be embarrassing if we didn't. Now, while you're looking at that, any guesses why we would flip the rows here when we're dealing with the inverse function? Why would we flip-flop those rows? Any guesses? Hint, it ties into something in that first way, that way 1. Well, what did we do in way 1? We took the original guy as ordered pairs. We interchanged the order of the ordered pairs. Now remember where the ordered pairs came from. Ordered pairs were your columns. So the first position of the ordered pair was in the first row. Second position of the ordered pair was in the second row. If we flip-flop the ordered pairs, that's the same thing as what? Flip-flopping the rows. So this interchanging of flip-flopping the rows right here actually flip-flops or interchanges or reverses or swaps the positions of all of your ordered pairs all at once. Now, here's the only downside of this. The only downside is it makes this now not in the correct format for your 2-row format. Specifically, the issue is your columns get scrambled. Okay? Because in your 2-row format, you have to have this first row in order. So for our case, in the order 1, 2, 3, that's set. It has to be that way. So any guesses how we would unscramble these columns? In other words, what should we write on that second row? Don't overthink it. We should get the same answer as before. So here, if you look for 1, you look where 1 is on the top row in that blue stripe. So we find 1 in the third position. Below 1 is a 3, so you just copy the 3 below the 1. In terms of where we look for the under the 2, we'll look for a 2. It's in the first position. We'll grab the 1 below that first position. And for the 3, we find the 3. It's in the middle position. Below 3 is a 2. So let me go ahead and tag what we did right here. So here we unscrambled the columns. And here we swapped or flipped the rows. And notice we get the exact same permutation function that we got before. Okay? So that's the way that it's typically done in when you're dealing with your permutation functions. Now, some people don't bother with this middle step. I would recommend when you're working through these, for at least the first time you deal with your inverse function, go ahead and do what we did right here with way 1. But the fast way that people will do it is what they do is notice this is just reading the original permutation upside down. In other words, bottom to top. So you can also do it really quickly where you write out 1, 2, 3 for the first row. The bottom row is simply find your 1. The entry above it is a 3. So we put the 3 right here below the 1. Find your 2. It's the first entry in the bottom row. Write it below the 2 right here. Find your 3. 2 is above it, so you write 2 below 3 down there. And that's also the way that you can write this. Okay? Questions make sense, kind of feeling okay. Want one more example, or does it make sense with what we did with the inverse? All right, seeing no questions from you guys, I'm going to assume everybody's okay. So let us look at something else that we can do. So something else that we do with permutation functions is the technical word is compose them together. And the only reason I paused on that is because of how they're written. So suppose we want to compose P1 with P4. And note, this is typically written as the two functions just side by side. Ooh, that is a good question. So the question is there a specific name for this unscrambled format? So this guy right here. No, this is just the standard two-column format. We will have an actual name for the other way of writing your permutation functions or your finite permutation functions, but this one here is just the standard two-row format. And the key thing to make it that two-row format is you need to have your building set that top row in order. So it's more of a description for its name as opposed to a really awesome, wonderful, short name. Actually, the other way that we write permutation functions also is a descriptor. It's called the cycle notation, and it's a description of what's actually going on inside of what you're writing as well. I wish I could say it was better. This first way, this scrambled form, this isn't any format. This is just scratch work. So it's basically the proper format versus the trying to get there format, if you will. I'm not sure that really helped, but that's sort of the idea here. Some people actually don't even have you do this step, but I have found that over the past times that I've taught this, that people definitely figure out what's going on better if you have this sort of middle step going on. All right, so to remind us in terms of composition, so let's do a brief aside over here. I'm assuming that all of you guys have dealt with compositions before, even if it's been a while. So for example, suppose you have something like, I don't know, x squared and 1 over x plus 1. Anybody remember what the composition of f and g would be? And it's okay if you don't want to try to type in what that answer would be, but what would be the format of what you would do? What would be the strategy of how you would find that answer of the composition of function f and g? Anybody remember that strategy? Or just the answer if you're comfortable typing it in. That works too. Yeah. So this one here is totally saying what? It's saying you're going to plug function g into function f. So this is the g function, the 1 over x squared, and then quantity squared. And you can totally do the same thing if you reverse it. And then I didn't reverse it for you guys. Just a second. You can say g of f. And in this particular case, you're plugging the opposite function in. And so you'd have, if you plug f into g, it would look a little bit different. Okay, so that's typically what you would see in a class prior to this one, something like, I'm assuming you've done an algebra class prior to this one, something that they would do in an algebra class. Okay, so what we're going to do, we're still going to do function composition, but notice we're going to be dealing with our two-row format. Our two-row format doesn't have a formula where you're going to build a new formula. We're actually going to have to track down what's going on with the specific elements, because we're really dealing with this fancy format that is really just giving you a bunch of ordered pairs. Okay, so here's what happens, and I'm going to attempt to Make it as clear as humanly possible. So, what this is asking us to do, the background, our P1 composed with P4 is literally telling you to what? It's telling you to plug P4 into P1 if we actually had formulas. Now, in terms of what? In terms of your actual elements, so with elements, what happens? If you plug in some value from your building set A, we would say we plug in that element A into the first function, the P4. Then whatever output we get from P4, we're going to plug into P1. So this is how it's going to track. I'm going to make a chart for us. We'll start off with A. We're then going to figure out what P4 of A is. And if that answer equals a B, B would then be whatever this number is inside of P4, but P4 says that number is supposed to go to. So this is the tracking work that we're going to be doing. Okay. Now, this is a little bit of the theory. Let's actually put this all together. Okay. So that's our background. So P1 composed with P4. I'm going to write them both down in their two-row format. So P1 was 1, make sure I get the right one here. P1 was 1, 3, 2. And P4 was the guy we actually just calculated. That was our inverse. So this is 3, 1, 2. Okay. Now, our final answer, and actually let me go ahead and give ourselves a little bit more space here. Our final answer will be still on that same building set 1, 2, 3, and we just have to figure out what are the specific numbers that we're going to plug in the second row. Now we've only got 6 options, so just straight up guessing gives us a 1 in 6 possibility of getting it right, but let's not guess. So here's what you do. We are going to work our way backwards. Now, why are we going to work our way backwards? It's because of the order of how the composition is written. Notice, what are we doing? We're plugging in our number into P4 first, but P4 is literally written second. So in terms of the composition, going the most inside the parentheses first and then working our way out is literally in the order of how you wrote over here to the side, the order of writing the F and the G. You literally deal with G first and then F. So you're working right to left instead of the normal left to right. Okay. So I'm going to put an arrow here so we don't forget which way we're working. We know we're going to start at the numbers 1, 2, and 3. So this is our scratch work to the side. The numbers that we're going to plug in to figure out for our answer for a composition are 1, 2, and 3. The first arrow is us dealing with the function P4. Okay? So according to P4, 1 gets mapped to 3. According to P4, 2 gets mapped to 1. According to P4, 3 gets mapped to 2. Not going to lie, I don't normally do it in this stage. I normally go all the way across first. So we can do that for another example. Okay? Now, once you've gotten to what P4 does with your original numbers, your domain, then you, in your composition, deal with P1. Okay? So this is like dealing with the inside function first. Now we're dealing with the outside function. So we move to P1. Here's P1. And P1 says if you start with a 3, you're going to end up with a 2. P1 says if you start with a 1, you're going to end up with a 1. And P1 says if you start with a 2, you're going to end up with a 3. Okay, so that's your scratch work to build your new permutation function. So if you take this information and put it over into your permutation function, just like when we built R2 back when we were dealing with relations, what happened? We then ignored the middle work right here, and we just grabbed the starting points and the ending points. Same deal happens. So if you start at 1 and progress through both of the two functions, you're going to end up at 2. If you start at 2 and progress through both of the two functions, you'll end up at 1. And if you start at 3 and progress through both of the two functions, you'll end up back at 3. Okay? It doesn't have to perfectly make sense right now, but can you guys follow it at least if somebody else does it? Any questions so far? Okay. So most people actually typically read this in the 2-row permutation functions. Most people don't do that scratch work to the side. But I have found that is definitely, percentage from getting up of reading it out of the 2 ordered pairs, 2-row, I can't speak today, 2-row format as opposed to that scratch work to the side. The scratch work to the side, if you actually write it out, it's close to in the 90 to 100% of the class will be able to get the right answer, as long as you don't do a silly mistake. Over here, it's down closer into the 50-60% just reading it off of this stuff, okay? Until you know what you're doing. Once you know what you're doing, no big deal. But let me show you how to read it out of the actual 2-row format, and then you can pick which way you want to do it. I would definitely recommend first couple of times you deal with these guys, go and actually map out, give yourself a little chart of what's happening. Trust me, it helps. Okay? So over here, what happens is, and I'm just going to pick on the first column right here, you start in this second permutation function. Notice you're working backwards. You then progress and follow the bunny trail. So you go down to 3, then you go over to where 3 is in the second permutation function, track where 3 ended up and followed 3 down to 2. And notice your end result, 1 gets tracked to 2 right there. I'm going to go ahead and highlight the 2. You do the same thing for each of the numbers, 1, 2, and 3, and you'll build up the 2, 1, 3. Notice it's the exact same work that you have over here in the chart. It's just all completely in that 2-row format. I do not care which way you do it, but like I said, if you've never seen this stuff before, which typically at this level you guys probably haven't seen this stuff before, most people find it much, much easier to get the right answer if you're dealing with that scratch work chart to the side. Okay. Now, that deals with dealing with these things in the 2-row format. Would you like to have an extra example dealing with the 2-row format before we move on? Actually, it's probably a good idea to do that. So let's just go ahead and do an extra example before we move on to the other format. And this time, let's get out of our building set of 1, 2, 3. Let's pull some other guys. Okay. So suppose you are asked to do the following. Find or compute p squared, where p equals, in terms of its 2-row format, 1, 2, 3, 4, 5, and then we've got 3, 5, 1, 2, 4. All right. Now, any guesses what we would do if we wanted to find p squared? Where here, new function for p, none of those original 6 that we've been working on, where p here is on the building set 1 through 5. And the second row is 4, 5, 3, 1, 2. Any guesses how we would figure out what p squared is? Don't overthink it. Well, p squared is just going to be p composed with itself. Now, why is this called p squared? Because we typically don't bother to write with the functions unless you're in an intro algebra class. We often don't bother to write that symbol for composition. We just put them next to each other and it totally looks like multiplication. That being said, there's never a problem with putting in the composition symbol, but if you see two functions that are next to each other, this composition is that operation that it's referring to. Weird, I know, it's a thing. Okay? So if we want to compute here p squared, what are we going to do? Well, we're going to be looking at composing this same guy with itself. So 1, 2, 3, 4, 5, and then 4, 5, 3, 1, 2, and just copy it down. So 1, 2, 3, 4, 5, 4, 5, 3, 1, 2. Okay. And I'm going to go ahead and do the same scratch work we did before. So that chart to the side. So what we're going to need to do is we're going to need to track where the numbers 1, 2, 3, 4, and 5 go. And because it's squared, we're going to need to go through our permutation function p twice to get to the final answer. Okay. Now our final answer is still going to be on the same building set, 1, 2, 3, 4, and 5. So that part we know, halfway done. Not really, that's almost none of the work, but in terms of writing out the symbols, half the symbols are there. So if we track what happens to 1, remember, we'll read backwards, although the nice thing about squared, guys, is because it's the same permutation function in the two positions, even if you forget and read the functions in the wrong order, you'll still should get the right answer. Okay. So here if we start at 1, 1 gets tracked to 4. Actually, let me go ahead and do this. So 1 gets tracked to 4, right there. Now, once you have 4, you grab 4 in the other, you grab 4 in the other permutation function, and 4 gets tracked down to 1. Okay, so 1 to 4, 4 back to 1. Then you move on, and that tells you that 1 goes to 1 in p squared. Then you move on to 2, so 2 gets mapped to 5. 5 gets mapped to 2. Okay, that's total coincidence, and that's going to make this example a pain in the butt as an example, but oh well. That's the problem with making up numbers off the top of your head. And notice here, what happens, we'll get that 2 gets mapped to 2 in p squared. Now, 3 gets mapped to 3 in the original. And then when you move over to the next guy, 3 also gets mapped to 3. So in p squared, 3 gets mapped to 3. So I'm going to throw this to you guys. What do you think happens if you start at 4? What number should I put here under 4 in p squared? And I realize as I look at your guys' answer, I'm not sure if the last answer was for a previous question or the current one. Awesome, for the current one. Yes. So same deal happens with 4. In the first permutation function, 4 gets mapped to 1. But unfortunately, 1 gets mapped to 4, so we get back to 4, which means in p squared, 4 gets mapped to 4. Now, here's an awesome thing about permutation functions. With doing exactly 0 work, not even looking at this line right above, I could tell you what number goes into this last blank. Any guesses why I would know what the number is that goes into that last blank? And I'm going to claim it's a 5. Any guesses how I could find a 5 with looking at nothing else other than this very last answer right here? Well, that is true. So 5 gets mapped to 2. 2 gets mapped back to 5. So it definitely is a 5. But the reason, there you go. Yes, so in terms of a permutation function, it's both 1 to 1 and onto. It means you have to have exactly one copy of your entries from your first row in your second row. We had the numbers 1 through 4. The only entry that was missing was 5. So the very last guy here is always going to be the one number that's not used yet. That's a shortcut to find your last entry. However, yes, you can also verify it by doing this right over here. Now this guy, while not what I planned it to be, because normally you have just a scramble of the numbers 1 through 5. There's 120 different permutation functions here. The likelihood of us getting this one particular one was pretty low, but it actually is a very special permutation. This was our identity permutation function. Okay. Let me write the word identity. Okay. This happens. It turns out if you keep on raising your original permutation to powers, keep increasing the powers, eventually every permutation function, if you keep going far enough, bump that exponent up high enough, will always get you back to the identity. Worst case scenario, this exponent might be much, much larger. In this case, it was really quick to get back to the identity. And we'll actually look at that a little bit later on. Okay. But this would be the third type of thing that we'll look at, which is you don't have two different permutation functions that you're composing together. You're composing a permutation function with itself. All right. Let us move on now to the second, which is the more common way of writing, the second way or the more common way of writing your permutation functions. And these guys are as a product of cycles. Okay. So here, let me just title this, Writing Our Permutations or Our Permutation Functions. As disjoint. And the key thing here is disjoint product of cycles. And this one here is the more common way of seeing your permutation functions. Regardless of where you see permutation functions the first time, it's pretty much always taught in the two-row format just because it's easier to see these guys in the two-row format. But in terms of seeing it used a lot, it's basically a shortcut way of writing the two-row format. Okay. So let's see how to do this. And it is easier to see how to write your permutation functions as a product of disjoint cycles if we actually work through an example. So let's actually start off with an example. And I'm going to pull a relatively long example just so we get a little practice here. And so it's not too small that you don't see what's going on. So our example is going to be on a building set of 6. So 1, 2, 3, 4, 5, and 6. Scrambled, we have on the second row is 2, 3, 1, and then 6, 5, 4. Okay, so that's our permutation function, and we want to write as a product of disjoint cycles. And we'll see where that name comes in after we actually do it. Okay. So here's what you do. Okay. Always start with 1. I'm going to do scratch work to the side. So you start at 1, and then you see who 1 is mapped to. So in this particular case, who's 1 mapped to? What do you guys think? 1 is mapped to who? And you're looking right up here. Oh, yep, 2. Now, here's the part that makes this a cycle. Now, who is 2 mapped to? So using the exact same permutation function, 2 goes now to who? You got it? 3. Then you say, all right, well, where does 3 go? In other words, you keep going until you can go no further. And as soon as you get back to 1, notice this looks the same format as when we're pulling cycles back from relations. It's totally where the naming convention comes back to. When you get back to your starting point, stop. Don't go further, although we will deal with those last 3 numbers shortly. Okay? Here's how you write it. You write down 1, 2, 3. Don't write down the repeated number. We're not going to write down any numbers more than once. And we're going to close off the parenthesis. Okay? Your book actually puts commas between the entries. The only time you have to put commas between the entries is if you have a 2-digit number, if it's higher than a 1-digit number. Okay? Then we're going to start this again. So let me tag this. This is the smallest number. This one here, we're now going to start with the smallest number not already used. Okay? So who's the smallest number that hasn't been used yet? Would be 4. So we're going to start our next cycle with a 4. And then we're going to repeat the process. So 4 gets mapped to who? 6, perfect. Now who does 6 get mapped to? Back to 4, and notice we started at 4, we just ended at 4, so that means that finishes off our next cycle. So in the cycle, we'll write out 4, we'll write out 6. Don't write out 4 again. And since we haven't used all of the numbers yet, we're going to go back and find the next number that we haven't used. So who's the next smallest number we haven't used? 5. Now, if you look at 5, 5 gets mapped to who? 5 gets mapped to itself, yeah. So we'll just write a 5 and we'll close off that 5. Notice what just happened. Let me put some terminology over here. That 5 is considered a 1 cycle because there's only 1 number in the cycle. The 4, 6 back to 4 is considered a 2 cycle because there's 2 numbers in the cycle. And the 1, 2, 3 back to 1 is considered a 3 cycle. Okay? Notice when you write these guys, each cycle is inside of its own set of parentheses. That's just to split it off from the other numbers. You only write your numbers exactly once, and how you order these guys is the smallest number that hasn't been written before is always that very, very first number in the cycle. So in each one of these cycles, the smallest number of the cycle is always written first. And if you look at all the first numbers, notice the 1, the 4, and the 5, that's written in ascending order. That's important. With disjoint cycles, technically these guys could be scrambled and it wouldn't matter, but as we move on, it's going to be important that we order these correctly. Now, in terms of writing this notation, 1 cycles have a tendency to not be written. Totally fine to always write them, but it's also totally fine to just leave them off. It's just like if you write 1 times x, people normally just write that as x. Same deal with your 1 cycles. They don't actually have to be written. Okay. Now, let us look at a couple of examples and then start looking at how we would deal with these guys with operations. So, actually, before we get into the next couple of examples, I want to draw this thing. So, as a relation. So this is a tie back to relations. Except, I'm not sure why I did a plural there. So if we looked at this guy as a relation, and there's no need to ever write out these ordered pairs, but if you did, it would be all the columns. So we've got 1, 2, 2, 3, 3, 1, 4, 6, 5, 5, and 6, 4. That was trying to be a 6, 4. Here's why I wanted to write it out as a relation. I don't care about the ordered pairs. I care about the digraph. Okay? Or specifically our directed graph. If we write these guys out. So 1, 2, 3, 4, 5, 6, trying to fit it in a relatively decent spot, and so you can still see the cycle notation from above. Why? Because I'm going to relate this back to our cycle notation. If we put in all of these ordered pairs, there's only 6 of them. Notice permutation functions, if you write them as relations or in the digraph, you're going to have a much smaller number of arrows. So let me put in these relations, and I'll get to your question in just a second. But the quick answer is yes. So the relation here, 1 to 2, gives you the arrow from 1 to 2. 2 to 3 gives you an arrow from 2 to 3. 3 to 1 gives you the arrow from 3 to 1. 4 to 6 gives you an arrow from 4 to 6. 5, 5 gives you a loop at 5. And 6, 4 gives you an arrow from 6 to 4. So, anybody notice a tie-in between your digraph and either your scratch work or our cycle notation from above? Notice our 3 cycle is exactly a cycle of length 3. Our 2 cycle, 4, 6, is exactly a cycle of length 2. And our 1 cycle is exactly a loop. It's actually where the naming conventions come from. Okay. So, in terms of answering the question, yeah, that's basically it. It is always appropriate to write your 1 cycles, but just because people have a tendency to be lazy and do shortcuts, if you do have a missing number, the missing number is considered a 1 cycle, and that's because with a 1 cycle, there's no ambiguity. It's just going to be these individual little loops right there. Okay? But yeah, if you only have a single number inside of your set of parentheses, a single number in your cycle, it's optional whether you write it or not. There's one exception to that, so since we're talking about it, let us look at that one exception. Suppose we go back and look at our function that we looked at a while back, so our identity function when we were on the building set 1, 2, 3. If we write this particular function as its product of disjoint cycles, notice what happens. Well, if we take our scratch work is almost more work than not using our scratch work. If you start at 1, well, you immediately end at 1. If you start at 2, well, you immediately end at 2. If you start at 3, you immediately end at 3. So this is just 3 1 cycles. Now, remember, we said 1 cycles were optional. It's true, except if you optionally don't write any of your 1 cycles, all of a sudden you have this equals a blank. That's not allowed. So your identity function is typically written as parentheses in just the first 1 cycle because you have to actually still write something down. And that would be the only exception where you have to write your 1 cycle is if you're dealing with this identity function right here. And this is actually why the notation for the identity function is this parenthesis 1 close parenthesis, not because there's anything special about that name, just because that's the disjoint cycle notation that corresponds to your identity function. Questions? Make sense? A little bit okay so far. So that deals with the crash course of what's going on with this cycle notation. Let's now actually see if we can do some operations when we're dealing with our cycle notation. And if you've got questions, definitely send them along the way. So suppose we want to do the following product. Actually, I should do this because this is something that you'll see. Suppose you have the following permutation function, and you decide that for whatever reason you hate cycle notation, and you want to rewrite this in the 2-column format because that's way easier to deal with how your brain is thinking. And that's totally fine. That happens all the time. It is way easier for me to type this cycle notation. So in terms of typed up things, you will often see this cycle notation from me. So anytime you want to convert it back to a two-column format, 100% fine. Okay, so this one, we want to go back to the two-column format. So first thing you want to do if you want to go back to the two-column format is you want to figure out what your building set A is. Why? Because that's going to be your first row. Anybody have a guess what the building set A should be? It's going to be 1, 2, 3, up to some highest number. Any guesses what that biggest number should be? It's definitely going to go up to 6 because you've got a 6 in the actual permutation function, but I'm going to claim 6 isn't the highest number. Yep, 7. Now, is 7 the highest number in those two cycles? It looks to me like it is. So unless you're told different, go up to whatever the highest number is in what you're given. So highest number in cycles. Now, nice thing is converting from that cycle notation back into the two-row format is actually easier than going from the two-row format into the cycle notation format. Okay? So remember what happens. The top row is whatever number you're starting at. Bottom row is who these numbers are mapped to. Now, remember the order that happened in the cycle notation. 1 is mapped to 3 because it's the number right after 1. So 1 gets mapped to 3. 4 is right after 3, so 3 gets mapped to 4. 7 is right after 4, so 4 gets mapped to 7. Now, any guesses what 7 gets mapped to? Any guesses what we should write below the 7? 7 being the last number in that cycle, in that first cycle. Or, properly spoken, the 4 cycle. Your only possibilities are the numbers 1 through 7 that we haven't used yet. Well, we'll come back to it. Okay. So if we then look in our second cycle, we've got 2, 6, 5 in that order. Ooh, there's a guess. Yes, you are correct. Now, why would 7 get mapped to 1? Because remember, this guy is a cycle. So 7 goes back to wrap around the end and come back at the beginning. Just like that. Okay. And that's why we call it a cycle. Cycle, think of it like a circle. You go around the wheel, if you will. I definitely pulled a bicycle in my head there. Sorry about that. All right. So if we look at our 3 cycle, we'll do the same thing. 2, after 2 is a 6. So 2 gets mapped to 6. After the 6 is a 5, so 6 gets mapped to 5. And after the 5 is a, well, at this point, we have to wrap back around to the beginning of the cycle. So 5 gets mapped to 2 exactly. Or, since it's the last number, the only one that's missing is 2. And that's how you convert back to your two-row format. No, you can also don't have to do it that way. You can also go through here and say, hey, 1, I found 1, 1 goes to 3. 2, find my 2, 2 gets mapped to 6. 3, find my 3, 3 gets mapped to 4. 4, after 4 is a 7, so 7 below 4. 5, after 5 is up, wrap it to 2. 6, after 6 is a 5. And 7, 7, wrap it to 1. You can also go in that order too. It doesn't matter. Both ways are perfectly fine. The one thing I would recommend, though, is write out the first row first. That way you know where you're going. All right. I've been talking about operations, and we've been not getting there, so let's actually get to operations. So, overarching directions for all of these. Compute the following. The first one is, suppose we have P equal to 1, 3, 2, 5, 4, 6. So that's its disjoint cycle notation. Q is 1, 6, 5, 3, 4. And what we would like to do here is find the composition. Now, it matters the order in which the composition, so I'm just going to do P then Q. Okay. So we have P composed with Q, or it's okay to write it side by side without the little symbol. In terms of writing it out, we have 1, 3, then the 4 cycle, 2, 5, 4, 6, then Q, 1, 6, 5, 3, 4. Some people like to actually do something like this, where they do some sort of little indicator where the P function starts and stops, where the Q function starts and stops. It turns out you don't have to do that. You can literally just put all of those little cycles next to each other. Now, in terms of reading this, you read it exactly the same way that you would previously, back to front or right to left. Okay, so exactly the opposite of how you would read words or English words on a piece of paper. Now, just like with the 2-row format, I'm going to do scratch work to the side. Now, just as a heads up, if you don't like what we're about to do, you can always convert both of these two permutation functions, the P function and the Q function, into the 2-row format and do exactly what we did previously. What I'm going to show you is how you deal with this multiplication, or really this composition, if you stay inside of the cycle notation. Okay. So here's the scratch work to the side. So in terms of our building set, the first thing we do need to deal with is what's our building set. Anybody have a guess what our building set is? Since I forgot to actually explicitly write it down. It's going to start with a 1, 2, and it's going to go up to some highest number. Anybody spot that highest number across these two permutation functions? Yep. So it's going to be all the numbers 1 through 6. And if you have one of the permutation functions goes up to a number that's higher than the other one, you can just assume you've got some 1 cycles in the permutation that went up to a smaller number. Okay. So what you do is you grab your building set off the highest number off of both of the two permutation functions. And something like a test, I try to make sure to give you what that building set is, but on something like homework, it doesn't always happen, especially if I'm pulling homework from like the book or something if he doesn't write it out. Okay. So what we're going to do is we're going to start from our building set or our domain, which is going to be the numbers 1 through 6. In terms of the first function that we progress through, we're going to be progressing through the function Q first. Why Q first? Because Q is the one that is on the right. Then we're going to get an answer, and after we get that answer, we'll progress through the P function. And if you don't bother to label these, you just track what happens to your number all the way through. Okay? You'll get the right answer either way. So if we start with the number 1, we read here right to left. So there's no number 1 in the first cycle. That's fine. There is a number 1 in this second cycle we get to. It's still inside of Q, no worries. So 1 here gets mapped to 6. Notice here, the 1 getting mapped to 6 is because 6 is after the 1 in the cycle. Now, you keep, in terms of the cycles that you visit each cycle in this right to left order, but internal to each cycle, you're still reading it in the same way that you would normally read things of left to right. So watch out, that can be confusing. Okay? Now, at this point, we're on 6, so we're going to track where 6 goes. Don't track where 6 goes when you're still inside of the Q function. So moving over to the P function, so the next cycle over, we see a 6. 6 here tracks 2 or gets mapped to 2. It wrapped around the end of this cycle. And once we get to 2, notice even if we progress to the next cycle, there's no 2 in that cycle, so we've stopped at 2. Okay. Good so far, okay so far. And then we can do this all the way down. Now, I'm actually going to erase something to make our life a little bit easier because this prep out is the right prep out if you're doing the 2-cycle notation. If you're doing the 2-row notation, if you're doing the cycle notation, it's a little bit easier to do it slightly differently. Okay? And I just prepped out too fast. So once you get whatever your answer is here for your 2, you copy that exact same number down right here, 2 again. So we're building our cycles. Right now we got 1. Then 1 got mapped to 2. So if you travel 2, look at 2. Currently we're at 2. 2 doesn't get mapped to anything here in this first rightmost cycle. So we move over. There is no 2 in the second rightmost cycle. So in the function q, there is no 2 visible, which means 2 had to be a 1 cycle, so 2 stays 2. In other words, it hasn't moved yet to another number. Now, keep moving to the next cycle. Third cycle we've looked at does have a 2. After the 2, there's a 5, so 2 gets mapped to 5. And as we go to the next cycle, there is no 5 because it's the only one in the p function. So that means 2 here got mapped to 5. In our actual work, 2 got mapped to 5, so we'll write 5 after 2. And then you see where 5 goes. So again, start at the rightmost cycle. There is no 5 in the rightmost cycle, so we move on. Next cycle we look at does have a 5. 5 here gets mapped to 1, so we write down a 1. Move on to the next cycle, which is now in our p function. We're currently looking at 1. There is no 1 in this cycle, so we move on. There is a 1 in this cycle, and 1 gets mapped to 3. Once we finished all the cycles and we arrive at whatever number we're at, that's the one that gets written after 5. So next we're going to look to see what happens with 3. So again, looking at the rightmost cycle, 3 gets mapped to 4 because 3 is actually in there. 4, excuse me, we're now dealing with 4. 4 is not in the next cycle. So then we move to the next cycle. 4 is in this cycle. 4 gets mapped to 6, so we're now looking at 6. Next cycle, 6 is not in this cycle, so we stay at 6. And this tells us that 3 gets mapped to 6. So then we look to see what happens to 6. No 6 in the first cycle. Next cycle, 6 gets mapped to 5. Next cycle, we're looking for a 5. There is a 5. 5 gets mapped to 4. So now we're looking at a 4. There is no 4 in the last cycle, so we stay at 4, which means in this product or this composition, 6 gets mapped to 4, so we write a 4 next. So now we're going to look to see what happens to 4. Where does 4 get mapped to? So again, looking at this rightmost cycle, we see a 4. So 4 here gets mapped to 3. We wrapped around the end. So now we're looking at a 3. There is no 3 in the next cycle, so we move. There is no 3 in the next cycle, so we move on down. There is a 3 here, and 3 gets mapped to 1. Now notice 1 here is exactly the same as who? Is exactly the same as our starting number 1. So don't write the 1 down. As soon as you get a same number that you've had before, that's where you close off the cycle. Okay? Now, notice at this point in time, what have we done? We've written all 6 of our numbers 1 through 6, so there's nothing else we need to worry about. If we'd actually closed off the cycle earlier, we would then look at the next number, smallest number that we haven't yet dealt with and started up our next cycle. Okay? And we'll do an example of that next time. So at the beginning of next time, we'll do a couple more examples of this guy. We'll actually get to the example that the Poll Everywhere question was talking about. So we'll deal with that one next time. So if you saw it and were like, wow, we haven't talked about that really because I don't know what K is or P is, that's okay. We'll talk about that next time. Okay. And then the second part of next time, we'll start talking about posets, which are another type of relation. They are normally not functions, but they are still another type of relation, and we'll be dealing with graphs associated with posets quite a bit. So those guys have picture representations where these permutation functions, technically you can draw the picture, but often you don't. Okay? But that is it for today. I'll hang out for a little bit if anybody has any questions, but there is no more. We are done.